All right, this is 3/5, the zeros of a polynomial function. Our one vocabulary word here is the multiplicity of a zero, and that is simply the number of times a particular zero occurs. And it is determined by looking at the exponent of the factor. That's all there is to it. All right, let's go over our definitions. Again, what is a zero? A zero is many things. Mathematically, specifically, it is the value of x that creates a y value of zero. Of course, we're using x's and y's, and that kind of gets some of y'all thrown off. But value of x, that'd be your input, your domain, creates a y, which would be your output or your range. Value of zero. Now, lots of things in math mean the same things, okay? They really do. We can think of things like this, that factors create zeros to some degree. They are synonyms with x-intercepts or roots. They're just another way of saying zeros. And you need to know all that. All right, next up is a power function. Power function is the first term when a polynomial is written in standard form. And it's big, it's important, okay? It really is. All right, moving forward. How are the zeros of a polynomial function related to an equation and graph of the function? What are the zeros of f of x equals negative 3x, x minus 4, and x plus 3 graph the property? So since we're talking about what the zeros are, we're literally saying that the output is 0, and this is going to enable us to use what we call the zero product property, right? And these are all simple. I mean, I also almost hate wasting time writing this down, but if negative 3x is 0, then x has to be 0. X minus 4 is a 0. Well, x has to be 4. And x plus 3 is a 0. Again, shifting, x is negative 3. If you hadn't figured this out by this point in time of the year, you ain't been trying too hard now, have you? All right, now, if the function was in standard form, what would the power function be, and how does it help? You don't have to do all the math, okay? You don't have to sit here and spend 20 minutes cranking out the distributive property and the double distributive property to figure this out. We're going to do some near math, okay? We're just going to multiply everything with an x together. That's how we're going to form a power function. So our power function is going to be the negative 3x times the x in x minus 4 times the x in x plus 3, and that's going to give us negative 3x to the third power. Now, why is that a big deal? Because I taught you end behavior. I doubt you remember it, but I taught you end behavior. What we have here is we have a negative x to the odd. And a negative x to the odd starts her day high and ends her day low. Now, how does that help me graph the function? Quite a bit, actually. It actually helps me tremendously. We're going to plot our zeros. We have a 0 at 0. We have a 0 at 4. Lost my place there. And we have a 0 at negative 3. This thing has to start high, and because the multiplicity of these things we hadn't talked about is just 1, we're going to pass through, rise up, curve back down, and drop back down to infinity. Because I knew end behavior, I knew the overall shape of the graph, and I knew how it was going to behave by and large. It's called end behavior. I'm not too sure what's going on in the middle unless I make a table. But I know by and large how the graph has to look. And that's the goal here. Rough drafts, rough drafts. All right, factor each function, then use the real zeros to sketch the graph. I wish I would have left some more space here on these. So these are factoring, and by God, I love factoring. Now, when I do the first one, I notice that every single piece is divisible by 4, and every single piece contains an x. So I'm going to pull the 4x out of each piece. Now, if I pull 4x from 4x cubed, I have an x squared. If I pull it from 4x squared, I believe I have plus an x. And if I take negative 24 and divide it by 4, I have negative 6. Because I learned my multiplication tables when I was in elementary school, just like you did. All right, now what's it take to make x squared plus x plus 6? It takes an x and x create the x squared. Factors 6 are probably 2 and 3. I need to add to 1. 3 minus 2 is 1. Ta-da! All right, let's set her equal to 0. Again, 4x is a 0. This is the one that a lot of kids struggle with. You know, I had a kid tell me the other day that x would be 2. Well, 4 times 2 is 8. X has to be 0 because 4 times 0 is 0. So I know that x is 0. Change sign to negative 3. Those are my 3 zeros. This is my power function, all right? That is an x to the odd. Specifically, it's a positive 4x to the odd. So this particular one is going to start its day low and end its day high. Plot our zeros and be done with this thing. We have a 0 at 0, 0. We have a 0 at 2, and we have a 0 at negative 3. And again, because I know the power function, I'm going to start my day low, and I'm going to end my day high. All right. Next up is x to the fourth minus 81. This is actually a difference of 2 squares, but, you know, just think, it takes an x squared and an x squared to create x to the fourth. It takes a 9 and a 9 to create 81. And this works. Negative 9x squared plus 9x squared is the 0x squared in the middle. So it's beautiful. But wait, there's more. Don't be the kid who tries to factor x squared plus 9. You obviously don't know how to factor. Factor that one. This is going to be an x minus a 3 times an x plus 3. And by the way, I say that. The only way you know this is that you sit down and try. But this is not going to factor. There's the full factorization of this graph. Now, these two zeros are pretty simple. This is x equals 3 or negative 3, just done by changing sign. Think about setting this equal to 0. Take away 9 from both sides. We get plus or minus the root of a negative 9, which is imaginary. So there's no real zeros there. All right, back to what's going on here. Your power function. The first term in standard form is x to the fourth. That is a positive x to the even. Think x squared. Starts high, ends high. Of course, this one's really simple. It's just a parabola. And I know that the y-intercept's negative 81. That thing's in standard form. If an equation's in standard form, the last number you see is always the y-intercept. And your roots were at plus 3 and minus 3. And it starts high and it ends high. So it's going to come in from up high. It's going to hit that y-intercept and look like that. And there you go, boys and girls. That is the graph of that one. All right, important little slide. Be right back. All right, how does a multiple zero affect the graph? It should say, how does the multiplicity of a zero affect the graph polynomial function? So here we have a function with no numbers, just letters A, B, and C, which represents the x-intercepts. A0, B0, C0. Now pay attention to the exponent. A has a multiplicity of 2. I wonder what's in this text box. Multiplicity of 2 has a turning point at the x-axis. If you look at B, it has a multiplicity of 3. Let's see what's in this text box. A multiplicity of 3 crosses the x-axis. C has a multiplicity of 1, and a multiplicity of 1 crosses the x-axis. What they're trying to tell you in this little presentation here, in this little slide here, is that even multiplicity touches the x-axis. An odd multiplicity crosses the x-axis. That's what it does. And that's all it does. And it's not a hard concept, but I'm convinced that kids don't know what even and odd means. Because, man, this is so hard for kids to grasp. I really think a lot of kids have no idea what even and odd mean. I really do. It is what it is. If you ain't figured out even or odd by 16, I don't think you ever will. Describe the behavior of the graph of each function at its zeros. All right, so again, remember we can find multiplicity by looking at the exponent. That's how we find it. So one of our zeros here is x equals 0. And that x is to the understood first power. So its multiplicity is 1, which is odd. Here's a 0. X plus 4 is the factor. So x equals -4 is the 0. And again, that x had an understood first power. So its multiplicity is 1, which is also odd. And here's the last one. X minus 1 is a 0, and x equals 1. And if you just look at its exponent, you'll find that its multiplicity is 4, which is even. So these odd ones, they cross, and this even one touches. All right, moving on. This one has zeros at x minus 1 equals 0, so x is 1. Its multiplicity is a 5, which is odd. That's going to be a cross. We have x plus 2 equals 0, so x is -2. And its multiplicity is 2. That's a touch. And then there's this guy. X squared plus 9 equals 0. X squared is -9. X is equal to plus or minus the imaginary root of 9. So x is equal to plus or minus 3i, which is not real. So you would never see it on a graph because it's just not a real 0. And we don't even talk about its multiplicity because it's not real. Easy peasy lemon squeezy. All right, what are all the real and complex zeros of the polynomial function shown in the graph? So you are expected to read a graph and be able to use that to do factoring. Wonderful. So I know by looking at this graph that there is a 0 at x equals 3. Since I want all of them, I'm going to take that 3 and I'm going to synthetically divide her out. Drop the 2. Remember your acronym from this. We did this Friday. Drop, multiply, and add. So we drop the 2. 3 times 2 is 6. If we add, we have -2. 3 times -2 is -6. If we add, we have 3. 3 times 3 is 9. If we add, we have 0. Remainder constant xx squared. 2x squared minus 2x plus 3 is the missing factor. Okay? Will it factor? No. It's not going to factor. There's no way to make that thing factor. So we get to do something else. Now, the reason I know it's not going to factor is because I looked at the graph. This 3 happens an odd number of times. It happens once, 3 times, and that's it because we have an exponent of 3. And it's not repeated. I can tell you that much. So what we're going to do is we're going to do the QF here. QF is for quadratic formula. And it goes x equals -b plus or minus square root b squared minus 4ac all over 2a. And there you go. That's what we're going to do. A is 2, b is -2, and c is 3. So opposite of a -2 is a +2, plus or minus square root. Good practice to wrap that thing in parentheses. Minus 4 times a, which is 2, times c, which is 3, all sitting pretty over twice a 2. Now, what is inside that radical? Inside that radical, this dude right here is going to be 4, and we're going to take away 24. We're going to have 2 plus or minus a negative root of 20, both pieces over 4. And here we have radical simplification. I was talking to Miss Farmer at Greenfield, and she's having the same problem as I am. Like, y'all just bleh. The root of a -20, first off, is imaginary. Secondly, it is the root of 4 times the root of 5, so it's 2i root 5. So x would be 2 plus or minus 2i root 5, both pieces over a 4. You can say all over a 4, or you can say both over a 4. And then you can do the reduction if you think about them both being over the 4. 2 over 4 is a half, 2 over 4 is a half. I don't know why I put the 1 there. I don't like the way I wrote that. I really don't. I root 5. So pay attention to this one. This had 3 answers. It's a fundamental theorem of algebra. We had that one from the graph, and there's 1, 2 answers there. Easy peasy lemon squeezy. Don't know why that empty page is there. What are the real and complex zeros of this polynomial? Use the zeros to completely factor it over the complex number system. Ought to be some good stuff here. It's factoring 101. Guess and check technique, the best one there is, contrary to what anybody else might say. It takes an x squared and x squared to create x to the 4th. Factors of 4 are probably just 1 and 4. Seems legit. I think it is. So let's see here. I need a -4 plus a 1 to make this work. And just like any really good factoring problem, wait, there's more. X squared minus 4 is x minus 2 times x plus 2. And then, of course, you have the x squared plus 1. Now, this right here is not factored over the complex number system. This is factored over the real number system. Because you can look at this and you can say x is 2 and x is -2. But what about this bruh right here? What about him? So we're going to use a little bit of the ZPP to figure this out. Let's say that x squared plus 1 is a 0, and it is because it's a factor. X squared is -1. X is plus or minus the square root of a -1. And, you know, that's what I is. I is the square root of -1. So x is plus or minus I. Now, if x equals I, x minus I is a factor. If x equals -I, shifting x plus I is a factor. So x plus I and x minus I are the 2 complex factors created from that one. And then you have your remaining factors that you already figured out. I love this stuff. By the way, if you don't know what the complex number system is, the complex number system is the set of all numbers, both real and imaginary. Now, is there anything else worth talking about on this slide? I don't know. Be right back. Good old Acme Innovations, kind of like Roadrunner. I don't know if you know those cartoons or not. Acme Innovations makes and sells lamps. Their profit P and hundreds of dollars earned is a function of the number of lamps sold in thousands from historical data. They know that their company's profit is modeled by the function shown. What do the zeros of the function tell you about the number of lamps that Acme Innovations should produce? Well, it seems to me that they'd want to do this piece right here because this represents profit above 0. So let's count the tick marks here. That looks to be a 3, 4, 5, 6, 7, 8, 9, 10. We want x to be a number between 3 and 10 because that is profitable. Now, x is in thousands, so we want to sell between 3 and 10,000 lamps. Oh, that's an easy question. But if they put something like this on your EOC across the great state of Tennessee, 70% of the student body will miss it. 70% of all kids in Algebra 2, not just Dresden High School. Dresden High School will be way better than that. But 70% of all students in Tennessee will miss a question like this. I don't think you know how to read. Prove me wrong. Prove me wrong. If somebody says like that, something like that, you've proven wrong. Due to a decrease in the cost of materials, the profit function for Acme Innovations has changed. Ruh-roh. Well, let's see what it looks like. Let's just go to our trusty TI-84 and let's push buttons. We got a -x to the 3rd plus 10x squared. That was not an x. Negative x to the third. What do we got? Plus 10x squared plus 13x minus 22. And again, play along. You see it, you hear it, you say it, you do it. Zoom 6. If we don't see what we need to see, we'll just do some else. Now, pay attention. This part of the graph over here is where you have negative x units sold. That doesn't make a lick of sense. You are going to play with a window. Let's go ahead and look up, I don't know, 50. And let's look right 20. See if we see a better picture. Because I'm interested in that curvature that's happening here. This should go up and then it should come down. It didn't go down. Oh, there it is. I'd still like to see some more of this. So let's change my Y max to 100. I feel like that'll do it. Mother of God, it didn't happen. Sorry to waste your time. It's not like you got anything better to do. Now do you? Sweet Jesus. Still ain't found it. All right. This is it. 250. There we go. That is the graph I was looking for. You should probably do a rough sketch. But anyways, let's see here. This looks like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That looks like an 11. X is a number stuck between 1 and 11. So in words, between 1 and 11,000 lamps is profitable. All right, what are the complex solutions of 2x cubed plus 5x squared minus 3x equals 3x cubed plus 8x squared plus 1, given that the one real solution is x equals negative 1? All right, well, our first thing that we're going to do here is put this in standard form. And I'm actually going to shift everything right because there's more x cubed on the right. So that's going to give me a 0 on the left-hand side. 3x cubed minus 2x cubed is an x cubed. 8x squared minus 5x squared is a 3x squared. And let's see here, the 3x gets moved over, changes its sign, and there was already a 1. Perfect. Now, I'm going to do something called synthetic division. Let's keep our coefficients here. 1, 3, 3, 1. X is negative. Acronym, DMA, drop, multiply, and add. I drop the 1, I get a 1. Negative 1 times 1 is negative 1. 3 plus negative 1 is 2. Negative 1 times 2 is negative 2. 3 plus negative 2 is 1. Negative 1 times 1 is negative 1. 0. That's what I was after. Remainder constant xx squared. I have an x squared plus a 2x plus a 1, and it is where the other zeros are, so I say she equals 0. Now, what do I want to do here? I actually want to factor it, because it does factor. I don't have to do the quadratic formula when I see something that factors. This factors is x plus 1 times x plus 1. Interesting. I was expecting there to be some imaginary answers, but there were no imaginary answers to this problem because this told me that x is negative 1. Now, when somebody says complex solutions, remember complex means real and imaginary. All numbers are complex, but this happened twice here, didn't it? X is negative 1, x is negative 1, x is negative 1. That's a 2x cubed. It had 3 answers. And what happened is x equals -1 has a multiplicity of 3. Weird, huh? But that one particular 0 happens 3 times. That's just where we happen to cross the x-axis on this problem. All right, what else we got left here? Oh, inequalities. Those are always wonderful. They're not hard. I'm not asking you to do this by hand. I'm asking you to solve an inequality by graphing. So really all you got to know is what it means to be less than 0. Being less than 0 means below the x-axis. So let's just take a look at this function. Now, I do also want to pay attention to this. This is going to factor as x times x squared minus 16, which is going to be x times x minus 4 times x plus 4. So pay attention to that too, because those numbers are going to play a big deal in the answer to this question. 0 is going to be a big deal. 4 is going to be a big deal. -4 is going to be a big deal. Anywho, we're going to graph this thing. I wonder if I should teach y'all how to do it by hand. I just don't know. Anywho, we're going to put the 0 on y2 in case we need it, which we don't, but we're going to put it there anyways. Zoom 6. And here's my graph. And I'm not going to play with the window because I don't need to play with the window. I went ahead and graphed y equals 0 to make it easier for you. We just want to be below the red lines. All we want to do is be below that red line. And the paths which we are below that red line, there's 3 pieces of this graph. One of them is actually doing this, going back up. This one's coming in from -infinity. Remember, this is x cubed. X cubed starts our day low, ends our day high. So this path runs from -infinity all the way to an x value of -4. So I know that x is less than -4, which I can also write as -infinity comma -4. This path happens between the x values of 0 and 4. 0 less than x less than 4, or union with 0, 4. There you go, kids. Easy peasy, Japanesey. All right, more of these. I think this is the last slide too. All these 3 contain an x. If I pull an x from 2x cubed, I have a x squared plus a 6x plus a 6. I don't think that thing's going to factor. I really don't think it is. It does have real solutions, but they're not pretty. So let's hit this. We have a 2x equals 0. So one of my values is going to be x equals 0. Let's hit x squared plus 6x plus 6 with the quadratic formula. X equals -b plus or minus square root b squared minus 4ac all over 2a. I'm using the smaller numbers, all right? So inside this radical is going to be a 36 minus 24, which is 12. Root 12 is going to be 2 root 3. See if you can figure that out. That's going to give me -3 plus or minus a root of 3. Now, the reason I did that is because the calculator is probably going to show us some answers and some decimals, and I'd rather have the perfect number as opposed to the non-perfect number. That's why I did that. I didn't do that to confuse you. I did that to get perfect numbers. All right, let's take a look at this thing in a graph. I'm getting wore out. It ain't even time for class to start. It's not a good sign. Probably did not expect this to take 30 minutes. I kind of knew it was. I anticipate this being a 2-day lesson. Because if it takes 30 minutes in a video, it's going to take at least 60 in class. So I should see this thing cross the x-axis 3 times. And the reason of course, I know what's going on ahead of time. Here's the only nice thing, is that piece right there. These guys, you can clearly tell, they don't quite hit the x-axis, now do they? Just because, second trace, since I've got that y equals 0 there, let me prove to you that the quadratic formula work we did was right. Enter, enter, enter. X is negative 1.268. Negative 1.268. We have a negative 3 plus a root of 3. And it's the same decimal, all right? It's just this looks prettier. That's why we're doing it. But anywho, let me go ahead and get a copy of my graph here. And we still have the same scenario. The scenario here was being less than 0, which is below the x-axis. And I see two pieces of this graph that happen to be below the x-axis. Of course, getting kids to write inequalities is always fun. Inequalities are answered with inequalities. But the two pieces are this piece and this piece. Now, this piece right here is where x is less than negative 3 minus a root of 3, or negative infinity comma negative 3 minus root 3. Good stuff. This piece is stuck between negative 3 plus root 3 less than x less than 0. Oh, that's hideous. Oh, that just destroys a kid. Or we can write it like this: negative 3 plus root 3 comma 0. Brutal, isn't it? Those funny looking numbers. And some of us don't even know what a square root symbol means. And you're in Algebra 2. I know you exist. You've existed every year I've ever taught. All right, let's do some more factoring. This is x plus 1 times x minus 1, but you ought to know that by now. This is x minus 3 times x plus 2. So these numbers are all going to come and play on my graph. Now, this is a greater than sign, so this is about being above the x-axis. And let's get to it. Go to y equals. Type our stuff in. This is going to be a fourth degree polynomial. It's going to start high and end high because x squared times x squared is x to the fourth. I haven't made copies yet today, have I? I need to be getting on that. You guys get to learn long division today. So there are three pieces of this graph that are above the x-axis. There's two pieces below, but there's three pieces above, and we're after the stuff above this time. Hopefully you can pick them out. You've got this piece, and this piece. This piece starts when x is less than, it looks like 2, which is one of my zeros, sorry, negative 2. X is less than negative 2. This piece is stuck between x values of 1 and 1. Sorry, negative 1 and 1. You can tell I'm tired. And this piece goes from 2 on forever to the right, so x is greater than 2. Those are the three solutions to this system. And I'm saying three solutions when reality is it's an infinite number of answers. If you like interval notation, this is negative infinity to negative 2, union with negative 1 to 1, union with 2 to infinity. And you should like interval notation. You should. You don't, but you should. And I think that's it. Oh, thank God it is. God bless. Y'all have a good day.